Okay, right? You can see it, right? Uh, okay, you can see the screen. What is?
Yes, Professor, we can see the screen.
Okay, good. All right, so well, for today, I'm going to review what you have previously learned in the first half. Okay, we will start from EOS because this is very important, right? Also, I try to cover the. Oh, I should remove this first. I will try to cover other parts also. Well, like give to him and also the basic uh, thermodynamics for phase equilibrium. Okay, so what is the definition of EOS? Actually, you see that before midterm you learn about EOS, right? Equation of state. So we need a model, a mathematical expression that relates. Okay, or describe the relationship between P, V, and T, right? P pressure, V is volume, right? And T is temperature, right? So you need EOS in order to relate all these parameter variables. Okay. And one important thing to, well, I have to emphasize this for P is intrinsic or extensive variable. Intensive or extensive variable. What do you think? It's intensive, right? So, but for temperature also, it P and T do not depend on on the size of the system, right? Even you have a large size of system, but if it's the same P, of course, it's the same P, right? Same pressure, also temperature, right? However, for V depends on the size of the system, right? You have larger size, of course, so V change, volume change. So we have both intensive and extensive variables here. And why do we need EOS? Because, well, we needed a relationship, right, between P and V and T, and also, well, we use it to predict thermodynamic behavior. Okay. So the most simplest one is ideal gas, PV right? So right here, you see that no N here, no mole. So we means, well, molar volume, okay? Volume per 1 mole, okay? So we have pressure, molar volume here, right? And what about R? R is a universal gas constant, right? It's a constant. Okay, so it depends on the unit of P, V, and T, right? And what about temperature? Temperature, of course, temperature is temperature, right? You can use Kelvin or Rankine is possible also. Okay, so for you see that for this is for ideal gas, and we have this assumption for ideal gas, right? Do you remember the assumption for ideal gas? Hmm? Still remember it? No? Okay. Anyway, for real gas, we need correction for this EOS. Okay. We will talk about the assumption for ideal gas later. Okay. One thing is P. You look at P. What happened to ideal gas? Hmm? For ideal gas, no interaction between molecule, and also, well, once the molecule hit the battery, it doesn't lost the energy, right? And the other thing is V. What about V? Volume for ideal gas? We assume that the the gas has no volume, doesn't consume any volume itself. I mean the volume of the gas itself. Okay. So, well, for example, if this room is your system, okay, if you assume that the gas here it's either gas, it doesn't consume any volume inside this, right? But so the volume of the system is the volume of the whole system. Okay. So you see that for real gas is not true because one thing is P, right? You have interaction between molecules. Also for V, the volume that the molecule can occupy, can move around, is not, does not equal V. Okay. So you need correction for all these terms. Okay. Okay, we need EOS for predicting thermodynamics property. And also, we need EOS to predict key property like enthalpy, entropy, and internal energy. Okay, all these thermodynamics state variables. Okay. Also, we need EOS in order to predict for the phase behavior like VLE, which is the important part for the second half. Okay. So we have several application of it, like chemical process design, natural gas processing, petroleum refining. Okay, now we for ideal gas. Okay, I told you last time is PV is equal RT, right? But this V is molar volume, right? It's extensive variable. It depends on the size of the system. If you replace this molar volume with the total volume, well, I use VT to represent the the total volume. Okay, you need size of the system here is N. Okay, is number of mole of gas in the system. Okay, but normally we omit N and then well we use V. Okay, which is molar volume. Okay, and for non-ideal gas, the most simplest way to represent the non-ideal behavior, non-ideal gas behavior, we can correct it with Z, okay, Z. We call it compressibility factor, right? When when Z is 1, okay, then it becomes ideal gas behavior, right? Okay, so this is the simplest way to handle non-ideality. Okay, so when we can be explicitly expressed as a function of P and T, okay, if we can write V as a function of P and T, okay. Also, we can write compressibility factor as a function of P and T, okay. And the other type of EOS is when P can be explicitly expressed as a function of V and T, okay. We can broadly classify the EOS as two types, okay. The first one is V is explicit, was it explicit function, and the second one is P is an explicit function. And have you heard about cubic EOS? Hmm? I
Yes,
think I think
yes,
yes,
Professor.
yes. In the first half, I think the before midterm you learned about cubic EOS, right? Well, all of cubic EOS is cannot well be written as explicit function of V. Okay, you see, but we can write as a explicit function of pressure. Okay, so cubic EOS is in this form. Normally, P is a explicit function of V and T, and in this case, of course, we can write compressibility factor as a function of V and T. Okay, so now let us compare between ideal gas law and real gas. Okay, ideal gas law assume no interaction between molecules and no molecular volume. Okay, this is one thing. So we need correction term for pressure and also volume, right? Okay, and real gas deviates due to intermolecular force and finite molecular volume. Okay, so but at high pressure and low temperature, real gas does not follow the ideal gas law. Okay, so the behavior of real gas come close to ideal gas when pressure is low, right? At low pressure and high temperature. Okay, and normally we consider pressure. If the pressure is low enough, then we can assume that the our system follow the ideal gas law. And what about limitation for real gas? Ideal gas law fail at high pressure, as I mentioned to you. At high pressure, intermolecular volume, molecular force increase. So one is increased, then it's deviate from ideal gas. Okay, and the next one is low temperature because at low temperature, attractive force dominates. Okay, and the other limitation is for ideal gas law at critical and supercritical region can, of course, it's totally fail. Okay, ideal gas law cannot be used. Okay, so in order to account for the what's it deviation due to intermolecular force and also volume change, the volume of the gas, well, we can use van der Waals. Okay, or also well various type of cubic EOS. And how can we do that? You look at the EOS first. No, not this one. Sorry. Okay. So the problem is on pressure and volume, right? So we need correction term for intermolecular force at pressure. And also for V, you need correction term also. Okay. Okay. So I will briefly explain about evolution of EOS model. Okay. And from ideal gas law to modern EOS model, how we develop, how people develop the EOS. Also, introduction of real gas model like Van der Waals, Reddish Kwong, and Peng Robinson. Okay. So, of course, early development, we start from ideal gas law first. And the limitation of ideal gas law is this one, PV equal RT. It works best at low pressure and high temperature, but it failed to account for real world conditions because of two things. The first thing is intermolecular force, and the second thing is molecular volume. Okay. So in order to account for intermolecular volume, no, intermolecular force and molar volume, the first one is correction of the ideal gas developed by Van der Waals, called Van der Waals EOS. Okay, it's more than 100 years, you see. Okay, for Van der Waals, of course, the we introduce the attraction we call A, and volume correction is B. Okay, this is the first EOS to predict critical points. Okay, so after that, we have reddish Kwong EOS. Okay, you see that almost 100 years after development of the van der Waals. The main feature of reddish Kwong is this model at temperature dependent attraction terms. Okay, so now A, the this one, the attraction or A is not constant anymore. It depends on temperature because it's temperature dependent. Okay, and by introducing the temperature dependent attraction term, we can largely improve accuracy of the moderate at the moderate pressure and also temperature. Okay, and after that, self modification of British Guang. It's the self British Guang. Okay, improve prediction for VLE. Okay, especially for hydrocarbon, and even nowadays still widely used. Okay, in oil and gas industry. And the other one is Peng Robinson. Also, this improved prediction near critical point. Yes, in this EOS can accurately use for vapor and liquid phase. Okay, and it widely used in natural gas processing. Okay, and recently is a modern advance like PC SAF. Okay, this one intends for target for complex fluid and polymer. Okay, this one is non-cubic EOS and used for highly complex system. Okay. Okay. Now we back to detail of the EOS. So if you look at the ideal gas law, we have PV equal RT, right? So you see that all gases, no matter is oxygen, is carbon dioxide, or methane, or any gas, all gases at the same T and P have the same V, right? Because you don't have any term specific for a particular type of gases. Okay, so all gas behave the same. Okay, but real gas, no. Different gases, even at the same T and P, have different volume and compressibility factor, right? So in order to account that, we can compare it with critical temperature because each gas has its own unique point of critical, okay, critical point. So we can use this term instead. TR is a reduced temperature. PR is a reduced pressure. We compare it with critical point. So TR is a ratio of temperature and critical temperature, okay? And PR, what about PR again? PR is a ratio, a fraction of pressure and critical pressure, okay? So our what's the assumption? The idea is most gases have the same compressibility factor at the same reduced temperature and reduced pressure. You see that paradigm shift for ideal gas, we assume that all gases at the same temperature and pressure have the same volume, right? Have same behavior. But once we shift to reduced temperature, we assume that any gases have the same TR and PR instead of T and P, have the same behavior. Okay. Okay, now we move to two-parameter law of corresponding state. Okay, we have two pure gases at the same TR and PR, okay, should have the same compressibility factor as I mentioned to you. Okay, now we move from temperature and pressure to reduce temperature and reduce pressure. Okay, so we can write generalized equation like compressibility factor instead of uh, compressibility factor is a function of T and P. Now its compressibility factor is a function of reduced temperature and reduced pressure. Okay, but we found that two parameter law of corresponding state, this one, this law, is found to be correct only for substance having either the same eccentric factor or critical compressibility factor. Okay, still, we found that we assume this, right? Uh, the gases have the same TR and PR should behave the same, but in reality, it's not true. Okay, we found that it behaves like that only when eccentric factor or omega or critical compressibility factor they have the same eccentric factor or critical compressibility factor. Okay, so we need one more parameter this time. Okay, in real life, the ZC of any gas is ranging from zero point 0.2 to zero point 0.3. Okay, so we can now we introduce one more parameter. Okay, now here we have two parameters, right? TR and PR, right? We add one more parameter. You have two choices. First, you can use eccentric factor. So compressibility factor is a function of TR, PR, and omega. Alternatively, if you don't want to use eccentric factor, you can use critical compressibility factor. Okay. Now, three parameter, TR, PR, and ZC. Okay. You can choose, okay, between eccentric factor or ZC. And we have three parameters now. Okay. So what does this mean here? From the ideal gas, all gases behave the same as the same T and P, right? For two parameter law of corresponding state, all gases with the same TR and PR behave the same. But for three parameter, all gases with the same TR, PR, and omega should behave the same. Okay? Or you can replace it, okay? Or vice versa, but omega or ZC, the same. Okay, so what does it mean for omega? Omega is an eccentric factor, okay, for spherical molecule, okay? We look at the geometry of the molecule of gases, okay? The spherical molecule are used as reference, okay? For spherical molecule, of course, omega becomes it's zero. What is spherical molecule? You have like molecule, well, geometry of molecule like sphere, okay? But if the molecule of your gas is quite complex and deviate from spherical, of course, omega change, okay? Omega is increasing, okay? So how we can, for other molecules means, well, molecule is not spherical molecules anymore. At TI is 0.7, okay? Log of PR set, it's -1, okay? So omega is -1 minus log of PR set, okay? So you use this expression in order to to find the omega, okay? You determine omega from this expression. For example, we want to determine the value of omega for water. Okay, given Tc at this second rate 47.1 Kelvin. Okay, and also uh, critical pressure also given. Okay, and you see at Tr it's zero point 0.7, right? We determine at this point. Okay, and temperature is we determine the temperature first. Okay, and you have to look. Wow, you have to consult the steam table. Okay, because you need vapor pressure. Okay, at this temperature. Okay, and from steam table, of course, vapor pressure of water at this temperature, 452 Kelvin, it's 10.02 bar. You need this information in order to find omega. Okay, so we substitute this pressure. We need pressure, right? And we have critical pressure here. So we substitute to this expression. Then you can find omega, eccentric factor. Okay, so for low to moderate pressure, we can write compressibility factor this way. Example, wow, that is 1 plus BP over RT, okay? I will tell you later because this is just brush up what you have learned, okay? So, wow, this one, we got it from Whitewell equation, okay? And, wow, Pizza et al. Proposed this one, right? B PC over RTC, it's B0 plus omega B1, right? And also, well, Pizza et al. Proposed how to find B0 and B1 here. Okay, you just replace it. Okay, and you see that B0 is a function of TR. If you need temperature at that point, right? And you need, if you know temperature and also critical temperature, you can substitute this. You can find B0, okay? And also B1, okay? And once you know the omega, omega, of course, temperature, you know omega, right? Like the previous slide, I show you how to find omega, okay? Then you plug all these things to this equation, okay? You can find the compressibility factor, right? And once you obtain the compressibility factor, you can relate between pressure, volume, and temperature, okay? Okay, yeah. Okay, so from the previous slide, we substitute this term and this term. What is it? We have this term, right? And this one, it's this one. I mean, it's a BPC over RTC, right? Here. And it's separated into two terms related to B0 and omega B1, right? Okay. So you can write the compressibility factor as a function of TRPR. Yeah. Okay. And there's a eccentric factor here. Okay. So let me repeat again. Ideal EOS, all gases at any temperature and pressure have always compressibility factor of 1. Okay. And for two parameter law of corresponding state, all gases at the same TR and PR have the same compressibility factor. Okay. And for three parameters law of corresponding state, all gases at the same TR, PR, and the same omega or the same ZC have the same compressibility factor. Okay. Okay. And the other type of EOS is viral equation of state. Instead of writing PV over RT as a compressibility factor or Z, we can write that one as on the left hand side, of course, is PV over RT. But on the right hand side, instead of writing compressibility factor, we can write that Z as a 1 plus B over V C over V square or D over cubic V. Okay. Of course, if you need more term, of course, you can write more, but it becomes too complex. Okay. We express all this as a power series expansion in terms of molar volume. Okay. So this one we call viral equation of state. Okay. Each term represent the interaction between molecules. This is one molecule, two molecules, and yeah, more. So first viral coefficient is 1, right? Always 1. It's starting from compressibility factor. Okay, it's represent the ideal gas behavior. Of course, if for viral equation, if you don't have this term, if B, C, and D are 0, the compressibility factor is 1. Okay, then your system becomes ideal gas. Okay, and for second viral coefficient, B as a function of T represent pairwise interaction between molecules. Okay, interaction between two molecules. And for third viral coefficient or C, normally we write as a function of T. Okay, it's not constant. This term accounts for three body interaction. Okay, at higher density. Okay, so for viral EOS is useful for low to moderate pressure, not at high pressure. Okay, and less accurate at high pressure where interactions are more complex. Why? Because once you have at high pressure, the molecule become more closer, right? So you need more term because interaction of, well, between multi-molecules becomes more and more. Yeah, it becomes higher. Okay, so you need more term, right? Okay, so for ideal gas, if you use viral equation of state, for ideal gas, there are no interaction, right? B, C, D's are all 0. Okay, and for this one should be real gas. Okay, without D. There are interaction between each gas molecule. So you have to consider this one. So that is a 1 plus BOV, right? COV square, DOV cubic. Okay, this is viral expansion in terms of volume. Okay, but actually you can write the viral equation as a function of pressure. Okay, instead of volume. Okay, so for this one, compressibility factor equals 1 plus BP CP square the plus the P cubic. Okay, this one is viral expansion of in terms of pressure. Okay, and you see that once pressure at very low pressure, P approaching zero, right? What happened here? P approaching zero, so this term becomes lesser, okay? Close to zero. This one also close to zero. This one close to zero. So you see that compressibility factor, it's one, okay? Becomes one, which is close to ideal gas, right? Or volume, okay? Once pressure approaching zero, that means, well, volume approach infinity. And if B approach infinity, this term becomes zero. This term becomes zero, right? B over V is zero. C over V squared is zero. D over V cubic also zero. Okay. That means, well, compressibility factor close to one. That means behavior of your system close becomes like ideal gas. Okay. One example. Let us compare the following viral expansion in terms of volume and in terms of pressure. Okay. You can write as a, well, and mod case, and you can compare between B and B prime. You can relate between B and B prime. Okay. B prime is a parameter for pressure expansion, right? Variable equation expand depends on pressure, and for B it's a volume expansion in terms of volume. Okay. Then you can write, well, you can use the parameter, which is a variable equation for volume expansion in terms of volume, in the form of pressure form. Okay. Okay. So how can we calculate the volume, molar volume? Okay, using variable equation. We start from, well, let's say we use only one term. Okay. So if we use only one term, it's compressibility factor is 1 plus BP over RT, right? All you have to do is you calculate TR first, okay? And from TR and B0 and B1, okay? Then you calculate B using this equation. It's a pizza from pizza, right? Then once you obtain B, you can calculate V, okay? V is, well, B plus RT over P. Mhm. Or you can calculate molar volume using this equation, okay? This is also derived from variable equation. What is it different from the previous one? The previous one, this one and this one, what is it different? Hmm? This one, right, from this term. If we use two terms, Okay, the third variable term. Okay, then we can calculate this p from this term. Okay, the next one, if we start from this, we can calculate molar volume also. This is also a variable equation, right? In terms of v. Okay, and PV over RT, which is represent the compressibility factor, it's that equal 1 plus B over V. Mhm. By rearranging this, the second equation, we can write V square, it's RT V over P plus BRT over P, right? And you, in order to find the molar volume, you have to solve this equation. And this equation is quadratic, right? You have to find the root of this one. Okay. And now we have two roots of this from this equation. Okay. What does it mean? What does it mean? Add the same T and P, but we have two roots. That means, well, we have two possible molar volume. And what does it mean? Of course, at one state, the gas cannot have two different volume, molar volume. Hmm? There's only one root that is of physical significance. Just check it. Mhm. The other one is imaginary, which is does not exist in reality. Okay. Or if we use the third variable equation. Okay. Now we rearrange it. We obtain cubic equation. So what does it mean? Once we want to find molar volume, right? So now it's cubic equation. What does it mean? You have cubic equation. That means, well, you can have three possible roots, right? And what does it mean? Again, there's only one root that is of physical significance. You have to check it, okay? Which one it's the real one, okay? Okay, so if we compare between variable equation of state and van der Waals equation of state, okay? And normally variable systematically improve accuracy through coefficients, okay? We have coefficient of B, C, okay? And if we compare variable equation of state and cubic equation of state, cubic equation of states are simpler, okay? But variable equation of state is more accurate for near ideal gas. And we use in laboratory measurement of gas property, and it's useful for processes where gas exhibits small deviation from ideal behavior. I mean, variable equation of state. Okay, so the next thing is previously we consider only the pure gas. Okay, what about binary mixture? If we have mixed gas, okay, so for mixed gas, of course, you have different B. If you prefer to use variable equation, you have different B. You have different parameters for each gas. We can say, well, we can use this mixing rule. B is summation through I, summation J, Yi, Yj, Bij. Hmm. What does it mean? So, so B is Y1, right? B11, which is interaction between gas one and gas one. Of course, B11 is B1, okay? And the second term is Y1, Y2, B12, which represent the interaction between gas one and gas two, okay? So B12 and B21 is the same thing, okay? Later we can combine it, this term. And the last one, Y22, B2. Of course, B22, it's interaction between gas 2 and gas 2. Of course, it's the same gas, it's pure gas. So it should, wow, here we can write B as Y1 square, B11, right? Plus 2Y1, Y2, B12, plus Y2 square, B22, okay? Where B11 and B22 are parameter for pure gas. Okay, B1, gas one and gas two. Okay, and we can find B1 two. Of course, for B1 and B2, it's pure gas. You don't have problem at all. However, we don't know B1 two. Okay, we can find B1 two from this expression B1 two PC1 two RTC1 two. Okay, equal B0 plus omega 1 to B1. Okay. The problem is how can we find PC12? Because it's mixed gas. We don't know PC for each gas, right? So PC12 calculate from this. This is a TC12 first, okay? Mhm. Okay. For PC12, it's follow the same idea. Yeah, this is C12, PC12. Okay. This is TC12 first, this one. Okay. It's uh root of square root of a what's it TC1 and TC2. Okay. Times with 1 minus K12. Now problem arises because we don't know what is K12. Okay. So you need this parameter. If you don't know this parameter, you set it to be 0. Okay. And it's done. Mhm. Okay. Now we can find TR12. Okay. And what about omega 12 from the this one, omega 12? Omega 12, it's just arithmetic mean, okay? Omega 1 plus omega 2 and divided by 2, okay? And what about this one? ZC12, ZC12, just you find ZC1 plus ZC2 and yeah, average of it. And what about VC12? VC12, it's, yeah, well, VC1 power to 1/3 and plus VC2 power to 1/3, okay? Find the average and then you power to 3. Mhm. And the last one, PC1, 2. This is PC1, 2. Okay. And then you apply all these things to calculate B. Okay. Right. This B. Okay. Once you obtain this B, you can calculate that compressibility factor. Okay. Then you can relate between P, B, and T. Okay. Well, for mixed gas, the first one, you can use Wider equation here. The second one, alternatively, you can use pseudo-reduced method for binary mixture. Okay. For this one, you find TPC, P is standing for pseudo, okay? And you find PPC, okay? And also omega, okay? By using these expressions, okay? And what about TPR? TPR is, of course, once you find TPC, now TPR is T, a fraction of T over TPC, okay? And PPR also, P over PPC, okay? Then you apply on this thing to this expression. You can calculate the Z, or compressibility factor. Okay, the next one is we quickly move through van der Waals equation of state. I mentioned earlier that for either gas, you have P equal RT over V, right? And you need correction term for P and V, okay? The first one for P, in order to account for deviation from, what's it? Account for the intermolecular force. And here is a correction term for molar volume, for, no, molecular volume, okay? So here for van der Waals, A and B, calculate from this, okay? And you see that each gas with different TC and PC, okay? Each gas has different TC and PC, okay? So each gas behave differently, depends on its critical point, okay? The next one is Reddish-Kwong. For Reddish-Kwong, of course, we follow the same idea with van der Waals. We have correction term for pressure. We have correction term for volume, okay? For volume, of course, it's follow the same, okay? However, in case of correction term for pressure, it's follow different idea, okay? Use different idea. And you see that Reddish-Kwong adds temperature dependence to the attractive term, this term, okay? And also, while this parameter determined differently, okay, for A and B, okay, but we can calculate this A and B from TC and PC, okay. Okay, the next one, Peng-Robinson. For Peng-Robinson, again, we follow the same idea. We need correction term for P and B, okay. And for Peng-Robinson is widely used in natural gas and hydrocarbon processing industries, okay. And the way we calculate A and B are different, okay. And you see that, well, here, for attractive, for correction term of pressure, we, do you think that it's temperature dependent or not? What do you think? Yes, it's temperature dependent. Why? Because there's alpha here, right? And this alpha relate to temperature, okay? So it can translate to, what's it? Because this term accounts for intermolecular force, right? So you see intermolecular force, interaction between intermolecular interaction force depends on temperature, okay? And this is, well, also, what's it? M depends on this one, depends on the eccentric factor also, right? And this one is British Guang. Okay, you later you can find. You can try it by yourself. Yeah. Now, how can we apply on that thing to mixture, gas mixture? Okay. For A, you know what A is? A and B, all right? From Peng Robinson, well, other equation of state. We can calculate A for gas mixture and also B also. Right? And again, you see K12 here. If you don't know K12, just assume it to be zero. Okay. Okay, still, all the equation of state model may not handle highly polar substance or electrolytes well. Okay, you need more sophisticated equation of state. Okay, and future direction is advanced EOS like PC SAF. Mhm. Okay, so I must stop at this point. Okay, yeah, later I will upload. Okay, hopefully that well you can. What's it? I'm not sure about before midterm. Okay, hopefully that I can conclude some. Then you can have idea how to apply the equation of state. Okay. Okay. So sorry that I have to finish today. Okay. And of course later we have to find some time to what's it to make up our class because we lost 2 weeks, right, for Professor Twachai. Okay. 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 Thank you. So
อาจา
yeah,
รย์
we
คะ
finish it there. ครับ
ไฟล์วันนี้อาจารย์จะอัปโหลดให้ใน MyCourse View ไว้ใช่ไหมคะ
ใช่ครับเดี๋ยวช่วงอะไรนะช่วงวีคเอนแล้วกันนะครับ
ค่ะขอบคุณมากค่ะ
ครับสวัสดีครับ